Now that's what I call a rock video. Hi, my name is Katie. As you saw in that rock video, rocks and minerals come in all sorts of shapes, colors, and sizes. How did they get that way? The answer is in how they were formed. On Hawaii's volcano Kilauea, new rock is being formed. This red-hot lava is rock in liquid form. Hawaiian legend says it is Pele, the fire goddess, who throws the hot lava down the mountain. But scientists explain it another way. You see, the Earth has three main layers. The core, which consists of hot, dense, solid metal surrounded by liquid rock. The mantle, which is mostly solid, but in places molten, meaning melted. And the crust, which is rigid and rocky. Underneath Kilauea's volcano, hot liquid rock called magma pushes up from the mantle and squeezes through the crust. It spurts and oozes out of the volcano's top and sides. When magma reaches the surface, scientists call it lava. These scientists are collecting lava that may be 2,000 degrees Fahrenheit, hot enough to melt some metals. As the lava cools, it solidifies and turns black, forming rock. Here lava is flowing into the ocean, where it will cool, creating new land. Rocks formed from the cooling of molten rock underneath the Earth and on the Earth's surface are called igneous rocks. Here are some igneous rocks from around the world. Igneous is just one of the three main rock types. The three rock types are igneous, sedimentary, and metamorphic. Sedimentary rocks form when particles of rock, sand, mud, and bits of plants and animals build up at the bottom of lakes, streams, rivers, and oceans. The weight of the material on top presses down on the material underneath. Water seeps into the spaces within the material. This water dissolves and deposits chemicals, gradually cementing the rock together. Over thousands and millions of years, this buried material becomes rock, called sedimentary rock. You can see its layers here. And here. The third major rock type is metamorphic. Metamorphic rock is rock that has been changed within the Earth, usually under great heat and pressure. Both igneous and sedimentary rock may undergo change to become new metamorphic rock. Metamorphic rocks can also recrystallize, meaning they go through even more changes to become a different type of metamorphic rock. When people say something is set in stone, they mean it won't change. But that's misleading, because rocks and minerals do change over time. Some of these changes can take place within a person's lifetime, but many take place over hundreds, thousands, and even millions of years. In a process called weathering, chemical and physical forces break rock into pieces and change its shape and appearance. Rain and the acids in rain can dissolve rock. Rushing rivers and streams tumble rock, breaking it into smaller pieces. Wind carrying particles of sand works like sandpaper, smoothing and sculpting rock. By these and other methods, weathering tends to break rock apart. Layers of sedimentary rock can be changed into metamorphic rock. These and other rocks may be reheated and converted to molten rock, which may become igneous rock all over again. This web of processes is called the rock cycle. Broken apart, transported, cemented back together, heated, changed, melted, even spewed out of a volcano. A rock's future isn't set in stone, not at all. Now here are some rocky questions for you to think about. Why are the grains of sand on a beach so small? How is the polishing of rocks in a rock shop similar to what happens in nature? Would you ever want to go in person to see a volcano erupt? Imagine if rocks could talk. What stories might a rock tell?
Look at the size of that rock.
If you love digging deep to solve mysteries, you'll love this. Rocks, minerals, and fossils can be clues, and the mysteries they help solve are some of the biggest mysteries on Earth and beyond. Let's meet some mystery solvers right now.
A paleontologist is a scientist who looks at life of the past and its traces. You can look at actual fossils. You can also look at traces of life in the past. For example, dinosaur footsteps. But the reptiles I'm looking at are not dinosaurs. They lived in the seas. They were marine animals. When they died, they sunk to the bottom of the sea and got embedded in a very fine sediment. If conditions are right, not too much oxygen, not too fast decay, then the fossils can get preserved in that compacted sediment. Part of my work entails traveling to other museums and studying their fossils. What I do there is I take notes how the fossils look, I take measurements, and I also take molds of those fossils. As example of that one, this is a mold I took in Frankfurt. The Triassic reptiles that I look at, they went back from the land into the sea. And what I'm trying to find out is how this could happen. What were the changes necessary for a land animal to go back into the sea?
One of my main areas of research is looking at the moon. The moon, we believe, used to be part of the Earth and was ejected when a Mars-sized planet smashed into the Earth about 4.5, 4.6 billion years ago. And the pieces that were broken off from that went to form the moon. We can get an idea of this from the moon rocks that were brought back when the manned Apollo missions went to the moon. And NASA requires that we keep the moon rocks in a locked safe, and for security purposes, you think of the amount of money that went to get these rocks, they want to look after them. And actually moon rocks look very much like rocks you can pick up anywhere on Earth.
Mysteries aren't all moon rocks or ancient fossils. Some mysteries are down to earth and important in our daily lives. For instance, take this water I'm drinking. Like almost half of the people in the United States, I get my drinking water from groundwater, water that is found underground, in spaces between the particles of rock. Next, we'll hear from two geologists who help ensure that groundwater and my drinking water remain unpolluted.
This is called a drill rig. This is a very small one. Some of these go up to 50 or 100 feet high. This is a small drill rig with which we can put a well into the ground. And then we can sample the water and we can sample the rocks that are down there. By looking at the rocks that are down in this hole, we can see what the minerals are, what the rock type is.
I study the way chemicals move through a rock. One example is this is a fractured rock, a sandstone that happens to have a crack going through it. We call that a fracture. And chemicals tend to move faster through the fractures than they would through the main body of the rock. The reason why we're interested when we go to a particular site in finding out how fast chemicals will move through a fracture or will move through a sand is because we are concerned with whether or not an area is good for disposal of drums of chemical waste that comes from all our various manufacturing facilities. We're also concerned about facilities where there have been potential spills, whether or not these chemicals are going to get into people's drinking water wells.
Would you want to work solving rock or fossil mysteries? Let's hear what our scientists have to say about their work.
I like field work quite a bit. Climbing into the mountains, trying to hunt fossils, excavating them, bringing them back to Chicago. That's quite an exciting thing to do.
Being a geologist is exciting because you are actually at the frontier of research. You're looking at the different planets, especially the one that we live on, and trying to deduce the processes that have gone to form it. And when we look at those different processes that happened in the past, we can try and project to what's going to happen in the future. That's quite critical when we look at what we're doing to the planet.
When I was a little girl, I always enjoyed going on hikes and going camping and being outside. And I thought I wanted to do something in the environmental field right from the beginning. And so my choices were between biology, geology, or environmental science. I finally decided on geology because the study was always a puzzle. Always trying to figure out how a rock got to be there, or how contamination got to be in a particular place, or why a river was where it was.
When did I know that I wanted to become a geologist? That was when I was 5 years old, and I decided that I liked rocks, and I liked rocks a lot. My mother hated the idea. The garden was full of rocks, and from then on, at 5 years, when I found out what the word meant, I knew that I wanted to become a geologist. Rocks are neat.
Now that you've met our 4 mystery solvers, how about trying a mystery of your own? This is Devil's Tower. The tower is made of igneous rock, but the rocks at its base are sedimentary. Can you guess how Devil's Tower formed? Long ago, the land here was sedimentary rock. Then magma pushed up into that rock, forming a volcano. After the volcano cooled, the soft, sedimentary rock around it gradually wore away, leaving the volcano's hard, igneous core standing all alone. Now here are some other questions for you to consider. How is being a paleontologist or geologist like being a detective? What clues do geologists use in their work? How are geologists important to society? Would you enjoy a career working with rocks, minerals, or fossils? This giant mineral is Topaz, and it's a real work of art. But rocks and minerals can have practical uses too. Right now I'm looking at you through minerals. This glass is made from minerals. In a glass-making factory, quartz sand is melted together with other materials. This red-hot mixture is poured out. then rolled flat to form window glass. Glass can also be shaped and blown to form glassware. Different colors are made by mixing in minerals such as cobalt, copper, and iron. Another widely used mineral is gold. Gold isn't just used in jewelry and art. It's in dental work, in solar panels and spacecraft and satellites, in electronics, in firefighters' protective visors, and even on the glass windows of this building. The glass is coated with gold, 1/1,000,000th of an inch thick. At that thickness, gold is transparent. A gold coating keeps out much of the sun's radiation, so a building can stay cool in the summer. Many minerals other than gold are useful in our daily lives, like the aluminum used to make the soda can. Don't forget, metals are made from minerals too. Steel is made from iron ore. This iron ore is mined, then broken into smaller and smaller pieces. Electromagnets help separate the iron from the other material in the rock. Later, the iron is combined with other materials into pellets that are used to make steel. To gather the rocks and minerals used to make steel and other products, people must mine. That takes energy. And mining is a messy business. No matter how carefully it is done, it disturbs the Earth's surface and the plants and animals that live on it. So how can people get the rocks and minerals they need without making a mess of the Earth's surface? Some people have suggested mining on the moon. But at the moment, that doesn't seem very practical. Some people are replanting and restoring mined areas. But this can be difficult and expensive. And others are recycling, which saves energy and reduces the need to mine minerals. Recycling doesn't just work on cans or bottles. For instance, it's actually possible to reuse and recycle many metal parts of this car. Even the asphalt I'm standing on, which is made from rocks, can be broken up and reused for paving. Now here's some other rock and mineral questions to think about. What rocks and minerals are important in your daily life? Why do you think it takes so much energy to mine rocks and minerals? How do you think people could reduce the need for mining or make mining less damaging to the environment? Do you think it would be desirable to do away with the use of rocks and minerals entirely?